Hey everyone, this is Abhilasha AKA TheTechGirl, and welcome to my special math series for all my younger brothers and sisters who are preparing for their 10th board exams. I know math can be overwhelming, but don't worry, this series is designed in a way to help you prepare without stress. Just a couple of hours a day, and you'll be exam ready. Today's chapter is the real numbers, and it carries around 7 to 8% of weightage in your exam. It is a simple chapter and easy way to secure marks, so let's get right into it. First classifications are natural numbers, which is normally represented by n. And the examples are basically it starts from 1, 2, 3, and so on till infinity. Okay? Examples are basically number of students in the class, or number of people traveling in a bus, something like that. Uh, it's going to be a particular number. It cannot be non-existent. It cannot be negative number. Okay. The next section is whole numbers. Is represented by W, and this is nothing but 0 plus n. So it starts from 0, 1, 2, 3, and so on till infinity. All the sets of positive number from 0 to n. That's the whole number. So basically, how many chairs are there in a hall? How many guests are in a hall, right? It can be 0. There are no chairs, so 0. And 1, 2, 3, 4. Next example is integers. Integers are normally denoted by Z or Z. Integers include all the negative numbers. So from negative infinity to, let's say, -3, -2, -1, 0, 1, 2, 3, till infinity. It's your bank balance. It could be negative, it could be positive, it could be 0, right? It could be nil. So bank balance is an example of negative numbers. You can also say all the negative numbers plus whole numbers is integers, right? The next set of numbers are rational numbers. You write them by Q. Rational numbers are all the numbers that can be written as P over Q, where Q is not equal to 0. Because when Q is equal to 0, it becomes not defined or undefined, right? Anything divided by 0 is undefined. So any number that can be written as P over Q, where Q is not equal to 0, that's a rational number. The next number is irrational number. Irrational numbers. It is represented by I. Numbers that cannot be written as fractions. Numbers. What are irrational numbers again? Number that cannot be written as fractions and have non-terminating and non-repeating decimals. What do you mean by that? So, first terminology is clear, right? It cannot be written as fractions. So it cannot be written in the form of P over Q. Okay. Second is it has non-terminating, non-repeating. The one of the most common example that comes into our mind is pi, right? Pi is nothing but 3.1415926, and so on. It continues and it's non-repeating. There is no pattern here. It's not like 3.33333. It's repeating. So this is not irrational. This is rational. But this is not repeating and this is not terminating. It's never ending anywhere. So 3.57, it's ending here, right? It's not repeating, it's ending. So, sorry, yeah, it's terminating and non-repeating, but it's terminating. So this is rational number. But this is not repeating. So this is irrational number, like golden ratio. What is golden ratio? Golden ratio is 1.618. No, 1.618 something something. So it's also, again, not repeating and not terminating. It cannot be written as fraction, so it's an irrational number. Any sorts of root, let's say root 2, root 3, root 7, these root of prime numbers, they are also non-repeating, non-terminating, fraction, can't be written as fractions. So they are also irrational number. These are the examples of irrational number. If we have to um, classify them together, right? So we can just rational number and irrational number together makes the real number. Real numbers are nothing but everything that is there on the number line. Every number that is present on the number line is called real numbers. So real numbers are nothing. Every number present on a number line. It can be fraction, it can be decimal, it can be root, square root, uh, cubic root, any sort of root value, anything. So all rational value numbers and irrational numbers are nothing but real numbers. Irrational number, we have multiple, which are whole number, integers, and natural numbers, right? So we can write like this is natural number, then whole number is nothing, 0 plus natural numbers, 0, 1, 2, 3, this is 1, 2, 3, 4. Integers is nothing but negative set plus whole numbers, and then rational numbers is nothing but integers and all others number that can be, because integers can be written as fractions, right? Any number can be written as a fraction. 5 over 1 is 5. Negative 5 over 1 is negative 5. It can be written as a fraction. It is an integer. It is a whole number. It is a natural number. So they're all rational numbers. And then there is a set of irrational number. All of them together makes your real number. So that's all about real numbers. Then the next part. Euclid's division algorithm is nothing but long division method. If you remember it from earlier classes, it's if you don't, it's okay. Euclid's division algorithm is a simple method we use to find HCF, or highest common factor of any two numbers. Okay, so HCF of two numbers. So let's say we are going to find the HCF of 56 and 12, right? So what we are going to do, out of the two numbers, we'll take the smaller number and make it a divisor. Okay, firstly, just to remind you again, divisor is this part. This is dividend. This is quotient. And whatever is left here is remainder. Okay, some people write this quotient here. That is also correct. Here is correct. That's okay. Now, we will take 12 as divisor, 56 as dividend. So 12 divided by 56 divided by 12. And then you do the division. 12 times 4 is 48. We are left with 8. Now what happens is this divisor becomes the dividend. And the remainder becomes the divisor. So like this. And then when you do this again, so 8 times 1 is 8. You're left with 4. And then you do it again, then 8, so 2. And 2 times 8. So your last number is 4, right? So your HCF of 56 and 12 is 4. Okay. Let's take one more example. Do it along with me. The HCF of 255 and 75. Okay. So smaller number is 75. So 75 divides 255. You get 75 times 2 is 150 and 3 is 225. So 75 times 3 is 225. You're left with 30. And then you do 75 twice is 60. Then you're left with 15, 30. Twice is 30. It's 0. You do it until you get your remainder as 0. Okay. So now your 15 is your HCF. So HCF of 75 and 255 is nothing but 15. Sounds good? Okay. So this is the method, Euclid's division algorithm. We use it to find HCF. The next important topic in this chapter is fundamental theorem of arithmetic. Fundamental theorem of arithmetic states that every composite number has a unique prime factorization. Now, it says it's unique. Okay, so it doesn't matter how you write it. So let's say you have a factorization of 15. What is the factorization of 15? 5 into 3. Yes. Now you can write it as 3 into 5. Doesn't matter. You can write it as 5 into 3. They are both same. They're unique. There is no such scenario where 3 into 5 will be any other number. It will always be 15. That's what fundamental theorem of arithmetic is. We use it to find LCM and HCF. So what you simply do is whenever you have a number, so let's say you have a number, you have to find the HCF or an LCM. Sorry, 1 second. HCF and LCM of 72 and 120. Okay. So what you're going to do is you're going to find the prime factorization for 72 first and then 120. So what are the prime factorizations? You do it 72. So you start with 2. This is nothing but 36 to 18 to 9, then 3, 3. You do it until you get 1. Prime factorization is nothing but set of prime numbers which multiply with each other to get you that number, right? The product of these prime numbers is going to give you that particular number. So that's prime factorization. So prime factorization of 72 is nothing but 2 into 2 into 2 into 3 into 3. Similarly, you do it for 120. You get 2, 60, 2, 30, 2, 15, 3, 5, and 5, 1. So you get 2 into 2 into 2 into 3 into 5. Yes? So your HCF here is going to be 2, 2, 2, and 3. So HCF is nothing but 2 into 2 into 2 into 3. Because common factor, right? So whatever is common, you're going to take. So 8 times 3 is 24. Okay? And your LCM is going to be whatever is common. Okay? And then 3 into 5. So It will be 24 into 3 into 5. So that is nothing but 360. So that's your LCM. Sounds good? Yeah? That makes sense? Okay. Now, the last topic in this chapter is the revisitation of irrational numbers. Basically, you have to prove that certain number is irrational number, right? So how do we prove that certain numbers are irrational numbers? Proof of contradiction. What do you mean by proof of contradiction? So let's say you have root 2 as a number and you have to prove that this is an irrational number. What you're going to do, you're going to assume, okay, we know that irrational number cannot be written as fraction. Irrational numbers are non-terminating and irrational numbers are non-repeating decimals. Okay. So non-repeating, non-terminating decimal numbers is difficult to write, but we can write it as a form of fraction. Okay, so we have to prove that root 2 is irrational number. How do we do that? We are going to assume that root 2 is nothing but a over b, where a and b are co-prime. Okay, it this way, and then square both sides. Then we get 2b squared is equal to a squared. Now, since 2 times b squared is a squared, that means a squared is even, correct? Therefore, a is also even. We can write a as 2k. Yeah. So now if we substitute that here, we have 2b squared is equal to 2k squared. And then we have 2b squared is equal to 4k squared, which is nothing but b squared is equal to 2k squared. Now we know b squared is also even because it's 2k squared. So b squared is also even. If b squared is even, that means b is also even. If a and b are both even, that means they have a common factor, which is 2, correct? Every even number has a common factor 2. That means they are not prime numbers. That's what we had assumed initially, that they are co-primes. So they are not co-primes, which is, so it is a contradiction to our assumption, and that's why our assumption was wrong. So root 2 is irrational. Does that make sense? Yeah. Another example we are going to take for this is 3 plus 2 root 7. Okay. Now, this is also an irrational number, right? But we have to prove it. So what we are going to do, we are going to rearrange it. We are going to say that, okay, we are going to assume that this is a rational number. If we rearrange 2 root 7, sorry. If we rearrange, then we have 2 root 7 is equal to r minus 3. And we know r is rational. We divide by 2. So we have root 7 is equal to r minus 3 over 2. This implies, because this is written in P over Q format, this is implying that root 7 is rational. But from the previous explanation, from the previous example, we know that root 7 is irrational, right? So this statement is contradicting the fact that root 7 is irrational. Therefore, our assumption was wrong, and 3 plus 2 root 7 is irrational number. So let's quickly recap what we learned today. We learned about real numbers and its type. Real numbers are every number that is present on a number line. We did rational numbers and irrational numbers. In rational numbers, we did whole numbers, natural numbers, and integers, right? Then we did Euclid's division algorithm, which we use to figure out the HCF of any two number. Then we did fundamental theorem arithmetic that is used to calculate LCM and HCF of any numbers. Then we did irrational numbers and how to prove them by contradiction. That sums up the first chapter, Real Numbers, of NCERT Class 10 book. And it holds around 7 to 8% weightage in the board exam. I hope you understand the chapter now and you are able to solve the questions. Yeah, now your task is to solve these 10 questions before the next video. Drop your answers in the comments and I'll see you in the next lesson. Until then, keep studying and all the best for your exams. If my video helped you in your preparation for the board exams, do like, share, subscribe, and comment and let me know. And also share this video with all your friends who are preparing for board exams and tune up for the next chapter in the next video.